Here comes the sky.
Force of gravity. Now we're going to learn what gravity is all about. As much as we know, anyway. We've learned that the force of gravity on an object, let's say mass m, is F sub g equals mg, where m is the mass and g is the strength of the gravitational field the object is in. But this equation is not universal. This equation does not work in all situations. In fact, F equals m times g only works when the object is near the surface of the Earth. Let's define near the surface of the Earth as being defined as high up as airplanes fly, as deep down as caves. So a little trick to remembering this is if we're dealing with F sub g, where g is lowercase, that's the little g, you can think about that as the weak gravity of the gravitational field. It's going to be the smaller one because when we deal with the more universal force of gravity, that deals with things typically on a larger scale like planets and things like that, so you would go with a capital G. If we're far from the Earth's surface, or not even talking about gravitational force of Earth to begin with, instead we're talking about the gravitational force that the Sun exerts on planet Jupiter. Big things, big G. For these cases, we need an equation for the force of gravity that works for all objects in the universe. This equation is Isaac Newton's universal gravitation, the law of universal gravitation. It's often said that Newton discovered apple fell on his head, but humans have known about gravity ever since there were humans to begin with. You're talking about nobody noticing that things fall down until 1687. Kind of silly. The actual folk story goes like this. Newton was sitting in the apple orchard and saw an apple fall at the same time as he saw the moon in the sky. This caused him to ask the question, why does the apple fall but not the moon? A lot more revolutionary to make that connection of apple falls, leaves fall, everything's falling, but that moon is stuck up there in the sky. So Newton drew on the work of Johannes Kepler, a German monk who studied the orbits of the planets around the sun. Between 1609 and 1619, Kepler formulated 3 laws that govern the motion of planets and their orbits. We're going to study these 3 laws later on in this unit. Very interesting stuff. But this is all to say that Newton used Kepler's discoveries, his own 3 laws of motion, and a mathematics he invented called calculus to come up with the following law of universal gravitation that gives the force of gravity between any 2 objects in the universe. We're not using calculus for this. No surprise there. But it is important to see what's happening here. If we have a big mass m and little m be 2 objects that are set some distance r apart, note that r is going to be measured from the center of one object to the center of the other object. The force of gravity, F sub big G, that the 2 objects exert on each other is given by this formula. F sub big G equals capital G, which is the gravitational constant, times the lower mass divided by r squared. The distance between those 2 centers squared. The gravitational constant is 6.67 times 10 to the negative 11 with this funky units here, newtons times meters squared per kilogram squared. To find this unit, you could multiply r squared and then divide by 2 m's and you would get this unit here. Some notes. The constant is called universal because it has the same value everywhere in the universe. Universal constants are called fundamental constants. That's not what Isaac Newton came up with. Instead, Isaac Newton came up with realizing that the force of gravity, force of attraction between 2 masses is proportional to the 2 masses multiplied by each other, and inversely proportional to the distance between the 2 squared. This is called the inverse square law. We're going to talk about that more in a little bit. The units for mass have to be in kilograms, and r has to be in meters for F to be in newtons. Because the constant is universal, it will be on the formula sheet, so you don't have to memorize it. but it kind of rhymes, so 6.67 times 10 to the negative 11th could save you a few seconds. See how, or if you have it programmed in your calculator, save you a few seconds. See how the force of gravity depends on the two masses and the distance. Force of gravity is directly proportional to each mass, an inverse square relationship with the distance. The same force, F sub big G, is applied to both m and little m, but in opposite directions. So we have the force of little m on big M, and then we have the force big M on little m. Equal forces, opposite directions, because Newton's third law still exists. On the equation sheet, of course, as usual, it might not look just like this, but the equation will probably look just like this, just not in the same place. Note the equation has absolute value bars around the F sub G, because it only gives the strength of the force, not information on the direction of the force. So what I was talking about with the big G and little g. Here we go. So we have F sub little g, and then we have little g here, and then we have, I think that's it. So gravitational force has the big G in it, so we know we're dealing with big objects like planets or satellites going around a planet, anything like that. Don't have to memorize the universal gravitational constant because it's there. Big G, 6.67 times 10 to the negative 11 cubic meters per kilograms times second squared. The force of gravity obeys an inverse square law. If the distance multiplied by 2, the force is multiplied by 1/4. In this animation, the force goes from 3,600 newtons at r equals 1 meter to 900 newtons at r equals 2 meters. If the distance is multiplied by 3, then the force is multiplied by 1/9. In this animation, the force goes from 3,600 newtons to 400 newtons. At 4, F is 225 newtons, 1/16 as much, and at r equals 5, the force is 144 newtons, 1/25 as much, because that distance has to be squared.